There is a place in Arizona where 6 million people a year walk to the edge, look down a mile into the earth, and say the same word. Incredible. Without stopping to think about what they actually mean by it. The official signs tell them what they're looking at. The result of the Colorado River cutting through rock for 6 million years. Most people nod, take a photo of the sunset, and drive home. But here's what's interesting. Among everyone who has ever stood at that edge, geologists, hydrologists, engineers, people who work professionally with landforms and know exactly what erosion looks like, several of them, independently, in different years, in different publications, recorded an observation that mainstream geology noted and never followed up on. The Grand Canyon does not behave like a river valley. It branches, not the way water branches, but the way a single structure in nature branches. A structure that follows the same mathematical principle from microscopic to planetary scale. And anyone who works with biological systems has one word for that structure: root system. Not a metaphor, a description of shape. And once you see it that way, the official explanation starts raising questions it hasn't answered yet. A river canyon is a technically defined landform with measurable characteristics. A river cuts through rock along the path of least resistance. It follows the slope. Its side channels form where additional water flows join the main channel, and the angle between the main channel and a tributary is governed by hydraulic law. In a typical river system, it runs between 45 and 70 degrees. That's measurable. It's reproducible anywhere on the planet. That's what water looks like when it cuts stone. Now look at a topographic map of the Grand Canyon from above. Not a photo from a viewpoint, but a plan view. Several of the canyon's side systems, the Havasupai system to the west, the Little Colorado to the east, branch off at angles and in directions that force the official model to build separate local explanations for each one. A different rock type here, a local tectonic shift there, an older watercourse of separate origin somewhere else. Every individual explanation exists. Geology has terminology for every anomaly in isolation. But when you take all those local explanations together and look at what they collectively describe, you don't get a system of watercourses of different ages and origins. You get a single branching network, growing outward from a central axis, narrowing as it moves away from the center, stopping not where the water runs out, but where the plateau ends. That is exactly, not approximately, but structurally, what the root system of a large tree looks like in a cross-section of soil. The walls of the Grand Canyon are as famous in the scientific community as they are among tourists. They expose a stratigraphic column covering nearly 2 billion years of Earth's history, and nowhere else on the planet is that much geological time readable in a single glance. But inside that column, there is a detail that geologists know well, and that almost never comes up in popular explanations of the canyon. Between the Cambrian layers, around 500 million years old, and the Proterozoic basement, around 1.7 billion years old, there are no rocks corresponding to that interval. The gap represents more than 1 billion years of geological record. It's called the Great Unconformity. It's documented, it's universally acknowledged, and it has no officially accepted explanation that fully closes the question. The prevailing position is that the rocks from this period either never formed here or were completely eroded away before the next cycle of deposition began. Both are technically possible. Neither has been confirmed by direct evidence strong enough to settle the matter. More than 1 billion years of Earth's geological record is missing, right here, in this rock, in this place. If you accept the hypothesis of a planetary-scale biosphere, this is precisely where its traces should have survived. That may be coincidence, but a coincidence with a specific address and specific dates is no longer just a coincidence. It's a question with a place to look for the answer. In 1869, John Wesley Powell led the first documented expedition through the Grand Canyon by river. 9 men, 4 wooden boats, 3 months inside a canyon no European had ever passed through completely. One of the last great geographical achievements on the American continent. Powell was a scientist, a geologist and ethnographer, and his records have the quality of observation that makes them a valuable primary source to this day. The expedition report was published, is freely available, and has been studied in detail by historians of science. It describes the rapids, the rock formations, encounters with Native American tribes, geological observations. But there are several passages in that report that standard retellings of Powell's expedition quietly set aside as insignificant. In several side canyons where the expedition went on foot, Powell notes a pattern of rock weathering that doesn't match any type of erosion he knows, and specifically records a difference in the density and character of the base layers compared to the rock above, a difference he cannot explain through the standard pressure of overlying strata. He's a geologist. He doesn't draw a conclusion, he records an observation he has no ready explanation for and moves on. That's exactly what makes these entries interesting. A professionally trained man, with no motive for sensationalism, encounters the same difficulty, in the same type of location, several times. And not one of those encounters became the subject of a separate study in the century and a half since the report was published. On April 5th, 1909, the Arizona Gazette published a story headlined, "Remarkable Finds in the Canyon." This is not a fringe source. It's a regional newspaper with a documented publication history, digitized and accessible through the Chronicling America project of the Library of Congress. The article describes an expedition funded by the Smithsonian Institution, led by a Professor Kincaid. According to the paper, the expedition discovered a branching system of caves extending horizontally deep into the rock wall of a side canyon, roughly 15 kilometers downstream from the mouth of the Little Colorado. Inside, rooms with regular rectangular outlines, objects of unknown origin bearing symbols the reporter couldn't identify, and bone remains described in the article as exceeding standard human size. The Smithsonian Institution does not confirm this expedition existed. The name Kincaid appears in none of the institution's documented expedition records. That's a fact. But there's one detail the skeptical argument doesn't fully close. The Smithsonian in the early 20th century actively funded fieldwork across the American West, part of which was documented irregularly and archived with significant gaps, something the institution's own historians have acknowledged. The source of the article is identified by name. No editorial retraction appeared in subsequent issues of the paper. The Smithsonian's response to inquiries about this specific expedition has been silence. Silence that has now lasted more than 100 years. For an institution that publicly and in detail addresses questions about hundreds of its other expeditions from that period, that silence about this particular case has a shape that's difficult to explain as simple oversight. There is a branch of mathematics called fractal geometry, the study of self-similar structures that reproduce the same pattern at every scale. Benoit Mandelbrot, who brought this concept into scientific use in the 1970s, worked extensively with coastlines and river systems, and showed that natural waterways have a measurable fractal dimension falling between 1.1 and 1.4. Root systems of plants have a fractal dimension in a different range, between 1.8 and 2.3. These ranges don't overlap. The gap between them is wide enough that a measurement will tell you clearly which type of system you're dealing with. Several researchers who applied fractal analysis to topographic data of the Grand Canyon, open data freely available through the US Geological Survey, produced results that were published, not in mainstream geological journals, which matters and reduces their academic weight, but the method is standard, the data is public, and what the analysis returns is this. The fractal dimension of the Grand Canyon's main system consistently falls between 1.6 and 1.7. That's not a river system. That's not a root system. That's the space in between, where the two explanations meet, where the available data is not enough to choose one and close the question. Not in a sensational newspaper article from 1909. Not in a 19th century explorer's journal. In open topographic data, processed with a standard mathematical method. That's where the unanswered question actually lives. There is a fact that is not scientifically disputed, and that has not been fully explained. During the Carboniferous period, roughly 300 to 360 million years ago, atmospheric oxygen reached 35%. Today, it sits at 21%. This has been reconstructed from isotopic analysis of amber and ice cores, and confirmed by multiple independent methods. Oxygen is produced by photosynthesis. A 35% atmosphere requires photosynthetic activity an order of magnitude greater than what exists today. And that's not an estimate. It's a direct consequence of chemical equations that don't change depending on whether the result is convenient. The official model attributes this oxygen level to vast swamp forests of lycopsid plants, reaching heights of around 45 meters. The model is consistent internally, and it's what the textbooks say. But atmospheric scientists working on deep time climate models have noted in their published work, not in fringe publications, in peer-reviewed paleoclimatology journals, that the numbers don't add up without assuming a global photosynthetic biomass significantly larger than what 45-meter plants could have produced at any reasonable estimate of their density and distribution. The plateau on which the Grand Canyon sits was located in the equatorial zone during the Carboniferous, where photosynthetic activity would have been at its highest, where biomass, if it existed, would have reached its greatest concentration. The Great Unconformity, that billion-year gap in the geological record, covers the period before the Carboniferous and extends deeper, which means that right here, in this rock, in this specific place, there could be traces of whatever was producing oxygen at levels the official model struggles to explain. Could be, if anyone looked. The Grand Canyon is not the only structure with these characteristics in the region. Bryce Canyon in Utah, a system of eroded hoodoos, vertical stone columns rising from the floor of bowl-shaped amphitheaters. Official explanation? Differential erosion of limestone of varying hardness. Standard geology, correct at the level of mechanism. But a plan view of Bryce Canyon reproduces the same branching architecture, the same angles at which side systems diverge from central axes, the same branching density per unit of area, the same narrowing with distance from the center. Antelope Canyon in northern Arizona, a narrow, winding slot in sandstone, officially explained by flash floods, brief and powerful water surges. That explanation holds for the upper layers of weathering. For the base structure of the slot, it holds less well. In cross-section, it's oval, narrowing downward, with smooth walls transitioning to a rougher base, a shape that specialists in biomimicry, the discipline that studies natural forms for engineering applications, have described in their published work as structurally identical to the cross-section of plant vascular tissue. That observation was published in the context of entirely different research, with no connection to the ancient tree hypothesis, which is exactly what makes it interesting. People were looking for something else, found this, wrote it down, and moved on. 3 structures in one region. 3 official explanations. One pattern that all 3 explanations describe separately and that none of them considers as a whole. The technology that could answer this question exists and is in active use. Muon tomography, a method for scanning dense geological objects using cosmic muons, produces a 3-dimensional map of the internal structure of a rock mass without drilling and without any destruction. In 2017, it was used to detect previously unknown voids inside the Great Pyramid of Giza. The result was published in Nature and is not disputed. The method has been applied to volcanoes, dams, and historical structures around the world. The cost of a single scan is comparable to the budget of an average university research grant. Applied to the walls of the Grand Canyon, this method would answer one specific question. Is the internal structure of the base layers uniform, or does it contain organized channels and voids that, at a different scale, would be indistinguishable from the vascular system of a living organism? This scan has not been done. Not because the technology doesn't exist, it does. Not because the canyon is inaccessible, it's a national park where research is conducted constantly. Because the question of whether a geological structure has a biological origin does not exist within the category system that geological science funds. A grant to study erosion in the canyon is available. A grant to test a root system hypothesis is not. Not because it's forbidden, but because it has never been formally proposed by any institution in a position to fund it. This is not a conspiracy. A conspiracy requires coordination and intent. This is the absence of a question, and the absence of a question is more reliable than any prohibition, because it requires no enforcement. Powell's journal exists and is published. His observations about the rock in the side canyons, rock with properties he couldn't account for through any mechanism he knew, are there and available to anyone who wants to read them. The Arizona Gazette article from April 5, 1909 exists and is accessible in the Library of Congress digital archive. The Great Unconformity, more than 1 billion years of missing geological record, right here in this rock, is documented and officially unexplained to a degree that would close the question. The fractal analysis of the canyon's topography, returning a value between the ranges for river systems and biological systems, was conducted on open data using a standard method. Muon scanning of the base layers has not been done. These are all facts. None of them individually proves what this video is about. But there is one more thing. In 1869, John Wesley Powell stood in a side canyon, looked at a wall of rock, and wrote down that he could not explain what he was seeing. He was the first trained scientist to stand in that place. He had everything he needed to ask the right question: the education, the time, the instruments, a published report that the scientific community was reading. He recorded the observation, put a period at the end, kept moving. And in the century and a half since, through every technological revolution, through satellite imaging, through genetic science, through muon tomography, no one went back to what he saw and asked, "What was that?" Not because the question is uncomfortable, because the person who would ask it officially hasn't appeared yet. The canyon is still there, the rock hasn't gone anywhere, and inside it, at a depth that can be scanned today without disturbing a single stone, is either what the official version says it is, or the answer to a question that changes everything we think we know about how long something was growing on this planet. One of those two things is true. We still don't know which one. Not because we can't find out, because we haven't looked.